Okay, welcome back to the second part of my talk, my contribution to the third Geometric Analysis Festival. As we mentioned before, we will see in this part the ideas of the proof. Okay, the ideas of the proof of this theorem. Okay. And just to give you a shot, we will prove first this part, that this is infinity, okay? That we cannot go down one step further the index of this upper bound, okay? This is the goal. And remember, this Kmax, this index is the maximum. This maximum is over the closed subgroup of G with dimension strictly less than the dimension of G, which is N, right? And well, because of the definition of Kmax, of course, there exists a closed subgroup of dimension Kmax minus 1, right? Because put the minus 1 there, and this maximum is realized in some H. And well, decompose G as H plus something, any complement, and each of these subspaces decomposes in one dimension in any way, okay, in one dimension subspace, right? And now we will pick this positive definite symmetric endomorphisms of G. Now that it's pretty simple, right? It has eigenvalues 1 here, because it's identity here, and it has eigenvalue s squared here, right? Here is what I mean. Remember, mu k squared are the eigenvalues of this. That's why I am putting here s in place of s squared, right? This is pretty simple. And well, to prove that this supremum is infinity, we will prove that for this particular curve with parameter s, when s goes to infinity, this term is going to infinity. Okay? And now that we want to prove that this goes to infinity, this limit is infinity, and now that this is equal to 1, right? According to this is 1. Yes, of course, because the dimension, the k max minus 1 eigenvalue is just 1, right? Because it has exactly k max minus 1. Well, this is 1, right? And well, we know I have to explain why this goes to infinity. And let me give you an idea, okay? And the point is, this is going to infinity, so the inner product induced by this positive definite symmetric map makes that any element, any vector G that has a non-zero component of B, when s goes to infinity, the norm of this vector is going to infinity when s does it. Okay? So if you now take a curve on the capital group G, and the velocity vector at some point has non-trivial component in this subspace, is going to be infinity. So in order you have a curve of finite length, when s goes to infinity, you have to, the velocity vector has to stay here, right? And if the velocity vector stay here here in H, this means that the group, if you start at the identity, for instance, the trivial element, you will stay always in H, okay? This implies that gamma of t is going to stay in H for every t, right? So you cannot join 2 points, the trivial element with some point outside of G, of H, with some curve of this kind. Okay, at some point you have to the velocity vector is going to have some non-trivial element in this subspace, and this makes that the norm, and then the length of the curve is the identity. Remember the length of the curve is, if you have a curve AB to G, well, the length is going to be the integral of the inner product with respect to this S, right? Or let's say GS. Okay, so if this is the square root, of course. So if this makes infinity at some point, the whole length is going to be infinity, right? So it is, I told you, it is a bit technical. Let's proceed. As a short, I give you again the same theorem, but I put in red the part that I want to prove, right? So let me prove that this is not bounded by a positive number when G is reversible. Again, we will find a curve of left-invariant metrics such that when t evolves, the time, or s is the time here, this is going to be 0, right? A curve GS. And then when this is going to 0, when s goes to infinity. Okay. There are, I already mentioned it, that there are two-dimensional subspace when G is semi-simple. There are two-dimensional or two vectors that generates the Holy algebra. Okay, so take H, a two-dimensional subspace that generate the Holy algebra. Okay, there is no any proper subalgebra containing H. And we define a sub, we associate to this. Actually, we can do this to any subspace of G, but let's do it with this particular two-dimensional subspace. The subbundle, right? Remember, we have an identification between the tangent space at this point and at this point, thanks to the differential of the diffeomorphisms of multiplying by at the left by G. Okay, so if you have the subspace here H, well, you can define in every tangent space, in the tangent space at any other point, this subspace, and this generates a subbundle of the tangent bundle. Okay, and because this is bracket generating, because this generates the Holy algebra, this subbundle is going to be bracket generating. Bracket generating for subbundles means that if you do the Lie bracket between elements in this subbundle, and then the Lie brackets between the resulting ones and the new ones, and then again Lie bracket and so on, and you span these subspaces, this gives you the whole tangent bundle. Okay, this means bracket generating in this situation. That's why we call bracket generating a subspace of G bracket generating if generates as a Lie algebra. This is equivalent for left-invariant sub-Riemannian structure. Okay, and a fundamental theorem in sub-Riemannian geometry is Chou's theorem that says that any 2 points in G, in the manifold G, capital G, can be joined by curves, by paths, smooth paths, such that the velocity vector is always in this subbundle. Okay, maybe it's not the geodesic for any metric. You have G and H, and maybe the path is something like this, and not this, right? But there is such a curve always with infinite time. G is compact, so it's going to be infinite. The supremum is going to be finite. And well, here is the idea. We write G as H plus something, any complement, and you write any of these two subspace as sum of one-dimensional subspace, and then pick phi s, a positive definite symmetric map, as this, the identity here, and a multiple of the identity, right? And again, we want to take the limit when s goes to infinity and check that this is going to be 0, right? And why is that? Well, know that this diameter is constant, right? Why? Because even if s goes to infinity, this makes that a velocity vector, a vector with non-trivial part in this subspace, the norm is going to be infinity when s goes to infinity. But you know by Chow theorem that there are curves only lying this, joining any 2 points, right? So the diameter, even if this goes to infinity, it doesn't matter because it stays in the same way here in H. So you have a positive upper bound for this diameter using curves, horizontal curves. Horizontal means that always the velocity vector always stays in this above. Okay, so this is bounded by some constant. We don't know the constant, but there is such a number. And this number is the third eigenvalue. Well, the first eigenvalue is 1, the second 1, because this is one dimension. But this third eigenvalue is s squared. And remember the mu3 is s, only s is the square root of this number. So this is s, the reciprocal of s, and this limit is of course 0, as we wanted. Okay? And now let me show you where we are. We have proved this and this already, and now we want to prove this. And I forgot to mention that we are going to focus on the estimates of the diameter, not on the first eigenvalue, which are a bit more technical. And the diameter is something more geometrically intuitive. That's why I wanted to focus only on it, right? Well, so to prove this, the upper bounds, we will find involved estimate. Remember a few slides in the first lecture we mentioned we call simple estimates to some estimate. Well, here are the involved estimates. So now fix again a left-invariant metric which is associated to some positive definite symmetric map. Again, find the eigen decomposition in one-dimensional subspace such that you have this, and remember the eigenvalues are mu k squared, right? And they are ordered and always positive. Okay. So if here is ak, hk, we define hk as the sum, this part. This is hk. And we define ck as this. Now that they have an intersection, ak. Okay. And well, the simple estimate, since we have this, and this is less than or equal to mu m, the simple estimate is to bound by mu m, every single index I, right? But here this is clever, and we do the same. For the first k, for the first k index, we bound mu I by mu k. And the rest are the same. And in the analogous way, in this side, we bound for I greater than k, greater than or equal, mu I is greater than or equal to mu k. So without only this and the rest, stay like they were, right? So we take common factor mu k here, and know that this number is less than or equal to 1, and this number is greater than or equal to 1, right? Because of this. And here is something strange, because we put a 0. And what means that epsilon k, that is defined as this, is symmetric map, but it's not positive definite anymore because it has eigenvalue 0, right? It's a positive semi-definite symmetric endomorphism. Semi-definite, because it's 0 on here is k, is positive until here. It's 0 in A1, AK minus 1, right? Here is a strict inequality. And here is something even more strange. It's a bilinear form, but it's not positive definite anymore. It's positive semi-definite. And here there is something even more strange, because we have an infinite value, and endomorphisms cannot be infinite value, right? Well, but let me write in this way. And please think this as a bilinear form, right? CK, right? And the idea is that these two bilinear forms are not inner products, correspond to non-Riemannian metrics. Non-Riemannian metrics. Well, this non-Riemannian, let's start with this, which is simpler in my opinion. You have an infinite symbol here, which means that if you evaluate a vector in G with non-trivial factor here, this means that the bilinear form has length, has norm infinity. Okay, so in some sense, it's like in geometric terms, it's like any continuous path cannot have velocity vector a term here, because otherwise it's going to have infinite length, right? And this is exactly what is the definition of a sub-Riemannian manifold. It's like the curves, the admissible path, are those such that the velocity vector always lies in HK. And what is going to be the inner product? Well, the fixed bivariate inner product restricted to this subspace. This is why this is the identity and this is not allowed. Right? I guess this is quite difficult, but for people with some knowledge, basic knowledge on sub-Riemannian manifold, this was easy enough. And this is, what about 0? We have we don't have an inner product, but we have a bilinear form. And what means this 0? Well, if you have a, geometrically speaking, if you have a path, a smooth path, for instance, with the velocity vector in this subspace, I mean in this subspace A1, AK minus 1, if you take the distance covered by this smooth path, it's 0. You go for free. Why? Because the norm of this, the velocity vector at every point, is going to be 0. So it's like there are some directions that you can go for free in this part, singular Riemannian manifold. The name singular is because a Riemannian manifold is non-singular, right? It's, the inner product is non-singular, but the name singular is because we have a metric which is singular, right? So in this case, there are some directions that you go for free. And in this case, there are some directions that you cannot go in this direction. This is the sub-Riemannian side, and this is the singular Riemannian side. Okay? And then this is a summary of the previous slide, just a summary. And what we obtain is that our Riemannian metric is bounded by mu k squared times this sub-Riemannian structure, and here singular Riemannian structure. Okay. So an extension of the previous lemma. Remember, we have a lemma such that we have a lemma at the beginning that if this happens, the same inequality with the diameter holds, and the reverse inequality with the lambda 1 holds. Well, here we have something similar. The diameter is the analogous, right? The diameter is set, this inequality stay with the diameter of this. This is the sub-Riemannian structure, the sub-Riemannian manifold. And the diameter, well, is the maximum between the distance of 2 points, and the distance is the infimum of the length of the horizontal curves shown in these 2 points. The maximum between any 2 points in the manifold. And here, this is the diameter, the maximum, but here is the one that you go for free in the orthogonal complement of CK. That's it here, right? So and the lambda 1, there is something analogous, but it's more technical. We don't want to enter in details. So two remarks here are that the bounds, these are the bounds, these numbers, the 4 bounds, they depend on phi. Remember, we fix a left-invariant metric, which is a sign of fixing a positive definite symmetric number. We fix this, and it has some decomposition, and these numbers depends on this decomposition. So they depend on the metric G. They depend on the metric. They depend on this. Okay, these 4 numbers depends on the metric, which is something that we don't want, right? And something else, well, more precisely, depends on HK and ZK. Depends in this, but which depends on the decomposition, right? And something else is that it may be the case that this bound is useless, because this might be infinity, right? If k is too small, if hk is too small, for instance, k1, you have 1 dimension, or for instance, you have k such that hk is not bracket generating. So you will not be able to join any 2 points with an horizontal path associated to this sub-Riemannian structure. So the diameter is going to be infinity because you cannot join 2 points, right? And analogous, this might be 0. Because, for instance, k might be very large. For instance, k equal to m. Ck is going to be the Holy algebra, and you can always join. This is going to be, when k is equal to m, is going to be the Riemannian case, right? The same here. Ck is equal to. Sorry, if k is equal to 1 here, is going to be the Riemannian case, and here, if k is equal to m, it's going to be the Riemannian case. But go back here. If k is equal to 1, this is the simple estimate. But if k is too large, it's because you have a lot of direction that you go for free. And if you have too many directions that you go for free, you are going to be allowed to join any 2 curves with distance 0. And this will imply that the diameter is going to be 0, right? So when this is 0 or this is infinity, these inequalities are useless. The same with the lambda 1. And the interesting point is that, remember, this is a positive number when k is m, and this is a positive number when k is 1. At some point, k is smaller than m. At some point, it becomes to be 0, infinity. And here, at some point, it becomes to be 0 when k is too small, and no, too large. And they are finite they are simultaneously finite only in this index when k is the smallest index such that hk is bracket generating. They are simultaneously positive numbers when k is this index, when k satisfies that hk is bracket generating. This subspace is bracket generating. Okay, let's know the consequence of this. We want to prove now this, right? So we want to bound really Kmax. So this is the statement that we want to prove, and we assume semi-simple, because if G is not semi-simple, Kmax is M. It's very easy to see that there are one dimensional one closest approach. So it implies that Kmax is M, and this is done because in the simple estimate. So let's assume without losing generality that G is semi-simple. And well, if you take a Kmax dimensional subspace, remember Kmax is this particular index. If you take Kmax dimensional subspace, this is bracket generating. Why is that? Well, suppose it is not bracket generating. It means that there is a proper subalgebra containing this H, right? But the dimension of this subspace has a dimension larger than this. So this implies an absurd with the definition of Kmax, right? So if you take a Kmax dimensional subspace, is bracket generating because how we define Kmax, right? And know that this is a symmetric space, right? The Riemannian space. And we will not use the symmetric structure, but we will use the topology, right? The topology of this set that is compact. This is a compact subset, compact space. But remember, because it's bracket generating, remember by Chau's theorem, it says that the diameter of this, of any sub-Riemannian structure, but we put this one, is finite because you can join any 2 points by horizontal path because it's bracket generating. Okay. So the involved estimate gives us this: the diameter of G is less than or equal to this term. We are putting k equal to k max in the previous slide, in the identity in the previous slide, and we have this, that the problem here, we already mentioned it, this depends on G, right? Because this depends on G. Okay. Well, but this is less than or equal to this, the supremum over every Kmax dimensional subspace of G. And this does not depend anymore on G, because you are taking the supremum over every subspace here. This does not depend anymore on G, but we still have to prove that this is finite, right? Okay, this is finite. This number is finite because this is continuous. This is compact, and because the functional that gives you associate to any k-dimensional subspace, associate this sub-Riemannian structure and take the diameter, this is a number, this is continuous. And because this is compact, this has a maximum, right? Why this is continuous? Well, to prove that this is continuous, it is enough to prove that the following application that assigned to a k-max dimensional subspace. This sub-Riemannian structure, not the diameter, the sub-Riemannian structure, is continuous with respect to the Gromov-Hausdorff distance. Why is that? Because the diameter is already, it is very well known that this continues with respect to this topology, right? So it is enough to prove this, and this is a problem, of course. I don't have any experience of this, but fortunately, I commented this problem to Enrique Ledonnet, and he studied the problem in collaboration with Antonelli and Golo, and they have a proof for this, that this is continuous with respect to the Gromov-Hausdorff distance, and it's going to appear soon in a paper that is still in preparation. Okay. Okay. And now let's prove the last part, the fourth part, which is this part. Okay. Here, remember, is the index 2 that we couldn't go up too much, right? The simple estimate put a 1 here, and here is 2. So let's prove this. And the involved estimate give us that the diameter of G is greater than or equal to this term, mu2, times this. Remember, what is this? Well, you have a metric such that on C2 is the same as the bivariate metric. You have a bilinear form that on this subspace is the same as G0. But on A1, which is the complement, this is 0. This is 0. So if you have a continuous path with velocity vector in A1, go for free. Okay? Or it has a component in A1. What it is really important is the component here, because this has norm 0, so it doesn't add anything to the norm. Okay? And of course, we want to prove that this is positive. This is bounded by a positive number. And in a very similar way as before, we take the infimum. This does, because this depends still on G, on the metric, right? Because it depends on the composition. But here we take the infimum in the Grassmannian space of codimensional 1 subspace, right? This has dimension m-1. And this does not depend anymore on G. And the point is, we want to prove that this is a positive number, right? But now that this has codimension 1, so you have only one dimensional direction that you can go for free in this non-Riemannian structure. Only one dimension. So the worst case, as a smooth path with velocity in one-dimensional space, if you reparameterize, is constant, right? Is you generate in a compactly group this path. The worst case is it is dense in a maximal torus. It is dense in a maximal torus. You cannot have a dense in the whole compactly group, unless G is abelian, of course, but let's stay in the non-abelian case. Okay, so this is the worst case, and that is like you can move, roughly speaking, you can move inside this maximal torus for free, but not in the rest. So if you want to go from the trivial element which lies in the maximal torus to an element outside the maximal torus, you will have terms in this. The velocity is going to lie at some point here. So the length is going to be finite. It's going to be positive, right? And actually, the lower bound is this number. Here is the homogeneous metric, is a flat manifold, right? is like on T, since you can go for free to any point among elements in the maximal torus, you quotient by T, and you take the metric in the orthogonal complement with respect to G0, and you obtain a positive upper bound, lower bound. Okay, and moreover, this calls for every maximal torus, and it is well known that the maximal torus are all conjugate. And this is by invariant, so it doesn't change this number for any t, right? So this number is positive and doesn't depend on g. Doesn't depend, because this is constant for every g, thanks to G0 is by invariant. Okay. So this ends the proof of the 4 facts. And now we end with some reference. This is the paper where is the conjecture, the important conjecture by Eldred, Gordini, and Salov-Coste, and they prove the case SU2. And I recommend also 2 talks, one by Laurent Salov-Coste and the other by Maria Gordini. They are available on YouTube or some other place, I don't remember. I will put these slides in my webpage. So, and there are links here if you want to go, but you can Google. And here, this is the paper, my paper, that this talk is based. And there is a continuation of this that works the same problem, but in the homogeneous case. What is the idea? In place of work in the space of left-invariant matrix on G, you have a K here, and you work on the space of G-invariant matrix on G over K. So you have the same problem, you have the analogous conjecture, and so on. And the main difference is that it was possible to prove in this extended conjecture many cases where the conjecture holds. Okay, and there is already a talk by myself available on YouTube if you wish to see more in this case. Okay, that's all, and thank you very much for coming until this point. I guess you are very tired. Thank you very much.